everyone, this is Justin Miller, Laboratories. It's the 8th of November 2016. I'm here with Derek Dollard, and we want to do a demonstration of what we've produced from this work episode here in fall of 2016. So I'm going to talk a little bit about the mechanical structure that we've got built here. This is an overground, what should be open wire line, and it's actually, we've strung this up with field telephone wire because we didn't have the copper weld that the phone company would have used for their open wire transmission line. So this actually will work out to our benefit for the time being, in that we've got two sets of pairs, twisted pairs on each crossarm, on each side of the crossarm. So this is what we got into. We've been at this for the last about 2 weeks, working every day just to string up this section. This is 1/4 of the intended finished line. This is what we were able to get put up in about 2 weeks. So those pairs from the cross arms come down the pole, conduit, and go into this terminal can here. And then from the terminal can, we've got it strung out on a piece of regular, what you would, household telephone wire pretty much, which allows us to take these signals into the car so that they can be analyzed and experimented with.
So these are the leads from our antenna. This is the earth connection, and these two leads here are connected to all these pairs are wound into, by zigzagging them back and forth, and the terminal cans are wound into a coil. So we initially should have had an 8-turn coil here, but brand new unused telephone, or unused raw field telephone wire, has strangely exhibited an open circuit. We have no idea why, but this is what happens when you're fighting revived junk. So we'll have to restring that wire. So on the outside we just paralleled the pairs. So basically here we have a loop going round and round and round, in this case 6 times rather than 8 times. Now if we connect these together, now what we've done, we hooked all the wires in parallel, and now we have a capacitor. So this one element of the Alexanderson antenna is about 1,200 feet in length. So multiply that by 4 sets of wires. You can see we already got quite a bit of wire into this. It's probably going to take 5 miles to finish the whole thing. Hopefully you don't have any more bad field telephone wires. It's not the end of the world. We'll just have to continue on at this point because the tensioning operation is so difficult that it would really screw us up. So we just wanted to get stuff working. So this is what we're connected to. Now also we can connect these two together and then ground the other end, and then what we have is a kind of coil where current's flowing over ground with all the wires in parallel going one way and coming back from underneath, usually about 3,000 to 25,000 feet. The return current comes up and we get that in the ground. So then we're operating as an earth antenna. And then we have our nemesis over here, the NEMV Energy harmonic transmitting power line, which completely overwhelms most of the reception here. But this will be an opportunity to learn ways to tune it out and to study the ever-increasing harmonic plague that's infecting the power grid. We're in an excellent position to do that here. So this is the test equipment. So this is what we normally use. Initially it's a Western Electric noise measuring set. This thing does is picks up minute signals in the background noise in telephone lines, and this is very similar to what we're doing here. That background noise that you didn't want in your telephone is exactly what we want here. So this thing's very sensitive. It's got a amplification of about 85 decibels. which is one with 8 zeros after it approximately. In this case, about 4 with 8 zeros after it. So this has got a lot of gain. And then we can listen, and it has a filter that we can get rid of all the Navy interference and the power line hum. Try anyway. So that's the first measurement. We did all these yesterday and documented all of it, so I'm not going to waste a lot of time in the video tuning around and writing numbers down. Today we're mostly after the sight and sound with the oscilloscope and what have you. So this is a small Navy portable oscilloscope. Very well suited for these things. I've been using them for a long time. Very reliable, compact, use very little energy. So that's going to show us our waveforms. And then we have a selective voltmeter, which basically is no more than a radio receiver with a calibrated output that tells you the strength of what it's receiving. And then we can tune in the Navy submarine transmit signal and the National Bureau of Standards time signal, which are the two prominent frequencies that operate in the Alexanderson frequency range. Okay, so we have one more device here. This is the audio device. This was built by Steve McGreevy especially for this project. We still have some bugs to work out, but we have yesterday did manage to get earth signals isolated from the power line signals, but we don't know yet if the earth is talking this morning, but it was going pretty good yesterday, and we did get some of that recorded. So basically, to start with, this is what we're up against. Power line hum. The speaker feedback problem here. There we go. That hum is what's plaguing us. Optimum. There we go. So this signal will overwhelm everything we're trying to do. What we're doing right now is this is picking up the electrostatic field of this 12 kV Y-connected power transmission line, and we can't receive the normal clicks and pops and whatever, because if we try to turn it up, the power line will just overwhelm it. So we're going to have to hook this device, we're going to hook to our antenna situation here rather than just the whip, and we're going to try to get these signals isolated out of the noise. So let's take a break. What we're doing is now we're measuring the hum noise electrostatically between the antenna as a capacitor and ground. So we're running a noise level of 50 decibels, reference noise, which is minus 90 decibels. So we're running about 40, a little bit of pick up there, about 40, minus 40 decibels with reference to milliwatt, which is about, we receive down on this level here. So the power line noise is 50 decibels stronger than the signal we're trying to receive, which makes it appear futile, but there's methods that we could do these things. So we get here's the sound. That's the electrostatic field generated by the power line. Okay, now what I'm going to do is now we'll operate the antenna as a magnetic loop, which will intercept some of the magnetic field of the power line. So we just got done sensing its dielectric field. You know, this is its magnetic field. So this one's about 10 decibels weaker, but that's because this thing is not really a perfect coil. It's arbitrary. It's not calibrated. So the sound has a similar nature. Okay, and then we'll take a break to get this set up to see what it looks like on the oscilloscope. Okay, now we have the scope hooked its neutral lead to the earth, and its active lead is now connected to the antenna electrostatically. We can connect these two parallel. It doesn't make any difference at this point. It's just a big capacitor. But so this is the electrostatic waveform on the scope of what's emanating from the power line. As you can see, it's filled with harmonics. These harmonics change on a daily basis, hourly basis, represent the parasitic power flow in the power grid. Okay, now we'll switch to the magnetic mode. This is the wave we're receiving magnetically. It's a lot weaker, so we've had trouble getting it without inverter interference. But again, you can see it's a harmonic waveform. It's beyond the range of the scope, its weakness. But we're looking at the harmonic component of it now. The 60 cycle wave it's too shallow to see. At this point, we need more gain, but we have the inverter problem. So basically that compares the electrostatic pickup to the electromagnetic pickup, which constitutes our interference. Now next we'll go to what kind of radio stations we can pick up. So now we have the antenna hooked to the selective voltmeter. So this thing right now is receiving with about a 3 kilocycle bandwidth at 15 kilocycles per second. So as you can hear, the earth is quite active in this band right now. I'm going to tune down, keep the headphone close by. Okay, now if we try to get down into the audio frequencies, first of all, let's see what our level is here. So we're set at minus 50 decibels related to 1 milliwatt, and we're running 8 dB lower than that. So this specifies with the terminating impedance of 600 ohms on this structure that we're receiving at about minus 60 dBm, which is what I was showing on the other meter That's kind of where our signal level is at, but the power line interference rides much stronger than that. So if we try to tune down into the audio portion of the band, we can start to see now instruments starting to become overwhelmed by power line harmonics. And so eventually that's all there is. So this is the band that we want to be listening, because that's where we hear, but instead we have the sounds of NEMV energy. So, but we know the signals. If we filter that out, we know the signals are here. So this is going to be the challenge, is to get that noise level down. So our calibrating station that we do our measurements on is there's a massive Navy transmitter, operates at about 2 million watts for communicating with actually not communicating, but broadcasting the submarines. So it's an extremely powerful signal, and we use that as a calibration reference. So every different configuration of the antenna, then we use this as our calibrator to tell if we're getting more gain or less gain, what have you. Now there's another prominent signal on the air. This one we don't have a BFO, so you can't really hear it very well. But this is a very slow digital code that transmits the time. Comes from a radio station called WWVL. Used to be under the direction of the National Bureau of Standards. Some other agency has it now. So this is when you have one of these radio electronic clocks that you don't have to set the time, and that it's always the second hand's right where it should be. This is the code that that clock is receiving, so that it knows exactly what time it is and can reset itself. So this one's operating at about the same level as the signals that we want to pick up down in the telluric band. And then let's see how strong the Navy one was. That was way up there. That one's over 10 decibels stronger. Okay, now we're going to see if we can get the actual earth signal separated from the power line in the next demonstration. We'll take a break. We used a output transformer for a carrier radio system, which has very bad low frequency response, but of course very high accentuated high frequency response. So now we've traded the power line hum for Navy transmitter overload. So that squealing you hear in the background is the Navy transmitter overloading the audition device here, but it gets rid of the power line hum enough that now the earth signals in the audio spectrum without translation from the selective voltmeter, we can hear them directly. So it is possible to build a network to eliminate a lot of the power line interference, and then it's also quite possible that we can feed the interference back on itself by receiving in two different modes and cancel it out. Good fidelity earth signal. I'm going to turn these around, which is take a break. I'm going to turn these around so we can listen to the other. Now we have the transformer out of the circuit, and we're just going straight. And we're using speaker amplifier control. The bit is a low pass or high pass filter. Got a spot in it that rejects the power line hump. So again, you can hear the earth signals, and this time the power line hum is the source of interference, but as of yet we do not have a filter to try to specifically eliminate that. But at any rate, the reception process is possible electrostatically, but as we will show in the next demonstration, to receive directly by the caloric mode here is impossible because of the massive power line interference. So we're going to demonstrate the level of that in the next section.
Now, I wanted to show you the other end. This is the current other end. Temporary dead end was established here because this is just as much as we could get done during this episode. So we were quite pleased that we were able to get this much done to allow us to do some basic experimentation, which we're showing you here in this video. So this is the mechanical dead end for this round for November 2016, and Eric's in the process here of hooking up a transformer to this end, this set of wires, and this transformer, what's the purpose of this transformer, Eric?
It's called a neutralizing coil. It'll allow us to ground the system without unbalancing the conductors. So this ground system, as you can see, is not protected yet, but it's going to take some more powerful equipment to get these things in the ground. This ground's not favorable to this.
Nonetheless, we were able to bash these ground rods in by hand. We got 2 on this side and 3 on the other side, which affects a reasonable ground for us. So this position ultimately is not going to be a dead end. Once we are able to continue, then the line will be constructed on out down to where we intended the real dead end. So this is actually about 1/4 of the way there.
So this section constitutes what's called the loading section. This is the key to the Alexanderson principle. Is the line is interrupted and goes into a network, and then is allowed to continue to the next loading section. This is loading section number 2. So to start with, the rolls of field telephone wire were 2 loading sections long, which is about 1,200 feet. So this is convenient that every other loading section then will be a point which we extract the signal or inject the signal into the earth for reception or transmission purposes, and have the ability to measure the propagation of the wave on the line and what have you. As this thing develops and the pole pair goes in, then we'll be able to actually physically measure what the velocity factors are to try to set the velocity factor to that where there is no velocity, where the whole antenna operates in uniform distribution, which is the fundamental Alexanderson principle that we're after, and that should reject a lot of the power line interference. So basically, because we can configure anything we want in these terminals and the networks that go inside, what we're building here is an analog computer similar to the one that was shown shown on the bench in an earlier video, but this is the actual distributed version with the ability to transmit and receive into and out of the Earth, and also into and out of the ionosphere. So now that we're grounded, we'll go back and take the measurements and see what we pick up. Okay, so right now we have our Earth connection here with our ground system, and then at the other end of the line it's grounded. So what we have is kind of a loop going over ground and then back through the underground, and as we can see, it's highly infected with NEMV energy harmonics to the point that we can actually receive it here on the Simpson meter as a measurable voltage. This is just one section, so there's actually usable electricity flowing in the ground underneath our feet, and the harmonic pattern of it is shown on the oscilloscope. You can see the basic 60 cycle wave, but the harmonics are greatly exceeding the strength of the 60 cycle wave. They're principally the third and sixth harmonics, and those are a very powerful source of interference, and it just shows you the sheer intensity of parasitic electricity that's flowing into the Earth because of the way the power grid is being reconfigured from a delta to a Y configuration. So this is, if we're receiving microvolts, and this thing's actually measuring 0.25 volts, where we're dealing with almost 1,000,000 to 1 voltage, or 1 billion to 1 power overload on receiving. So this is why these things are really supposed to be built in remote locations, but this was provided to us as the only thing around to work with, so we're stuck with it until we can get our more quiet locations set up, which is still going to have these things, but not nearly as bad because it's a properly connected power system that's delta configured, so we won't have any real problem receiving there. But it's a more remote location and difficult to deal with and less suitable for experimentation. So this is the experimental model here, and then that'll be the final application there, the noise-free environment. Okay, I'm going to put this on the other meter. We'll take a break. So now we're measuring the signal level of the stray ground currents from the power line. As you can see, it's almost to the maximum level of the instrument to be able to deal with the signal that strong, and our reception zone is down in here. So we're talking about the interference here is 10 million times stronger than the signal level because of the power line injecting stray harmonic currents into the Earth. So then I'm going to switch to this one next, and we're going to see how the radar reception works out in this particular mode, and if we can do some configurations with the filtering transformer to get rid of the power line hump. So let's see, we made this audible. Switch to the other instrument. So now we're in the radio frequency reception mode of receiving out of the ground, where before we were receiving capacitively. Now we're receiving conductively. So the National Bureau Standard Station is about the same strength receiving out of the ground, underground rather than the overground. The Navy Navy appears to be stronger. And then there's other, just for the hell of it, let's tune up the band and see what else we can pick up outside of the VLF. There's a distant LORAN station. They don't use LORAN in America anymore, but I believe they're still using it in Russia. Let's zoom further up and see what else we get. There used to be a European broadcast band down here, but the Europeans don't use amplitude modulation anymore. And this starts to get up into aviation beacons. Here's one identifying itself. Okay, now let's tune down into the Alexanderson band and see what the power company has to offer us. So, power line interference is more of a problem here. Starting to overwhelm the instrument to the point we get to about 5 kilocycles. The harmonics at 5 kilocycles from the power line are strong enough to overload the instrument, but it's still the earth signals are pretty prominent. I'll slowly take it down. Go as far as I can go. And I'll put this, try to put the transformer on it and see if I can filter that hum out. So we weren't successful in very much to get rid of the power line interference, but I will tune through and allow you to hear the spectrum of their signal. This instrument is not in the best shape, so it has, the meter will not read right down at the bottom of the band, but it still receives perfectly. So as we start to go down, start to get the first crackles of the harmonics, kind of instabilities and arcings and things latent in the power system. And we see it start to get around 3 kilocycles, which is right about the band that we want to start receiving in. That's when all of a sudden it starts to transmit. And you can hear all the intricacies of there, the parasitic power flows fighting each other and adding on top of each other. And it's really quite a mess. Utility companies are generating. There's another particular mode of its operation. And then we just get right down into the pure buzz. That's tuned right into the main harmonics themselves. 180 cycles per second and 540 cycles per second. So this is what we're up against in trying to receive these signals in any vicinity of power lines. We're actually not certain that all of this stuff is even coming from this particular power line, because even ground rods in remote locations indicate that there's a virtual feed from the power line here and hum, what have you, in the ground underneath our feet. It might be a way to tap it and get free energy. So that kind of wraps up the experiments to show you how far we've gotten thus far with what we've built. So I think enough interesting information has been gained, and we will continue at a later date when we have more elements added on. So that concludes this demonstration.